overlapping of valence orbitals in metal atoms according to molecular orbital theory. We will get valence orbitals with partially filled and some of the orbitals molecular orbitals, and some of the molecular orbitals are left vacant. So, this will give rise to valency band, and this will give you conduction band. If the valence band is partially filled, then it is conductor, then it will give conductance. If valence band is filled completely but conduction band is, if conduction band is very close, that means the energy gap is negligible. Valence band is completely filled but conduction band is very close, then transfer of ion, transfer of electron, transfer or movement or flow of electrons take place. This is the right. So, this is the case where this is completely filled. So, overall this is this is valence band, up to here it is filled but this is vacant, right. So, this is partially filled. And this gives us conductance because this electron can move over here. Valence band is completely filled. Valence band is completely filled. This is valence band and this is conduction band, but these are very close, no forbidden zone. Then electron. So, these two will give you conductance, right. But instead, if you have valence band like this and the conduction band is somewhere over here, where this is if it is like this, then this is huge large gap and this is a forbidden zone. So, the electron cannot flow into this conduction band, electron always remains in the valence band only, but unlike here electron easily flows into that conduction band. Here it is not possible as the gap is very large, right. Therefore, this will give you insulator, no conduction. And third possible case is valence band and this is conduction band, this is valence band and this small gap. So, excitation is possible and this will give you semiconductor. This is what the band theory of solids say, that due to the overlapping of atomic orbitals according to molecular orbital theory to give molecular orbitals, then the molecular orbitals formed will be of two types. One is a valency band and another one is conduction band. The molecular orbitals formed will get divided into two types of bands, conduction band and valence band. In the valence band, the electrons are present. If the valence band is partially filled, then electron flow takes place, gives conductance. Valence band is completely filled, but it is very close to conduction band, then also the transfer of electrons will take place, which results in the flow of electrons, that also will give conductor. But if the valence band and the conduction band, if the energy difference is very high, and if the electron from the valence band, which is completely filled, cannot move on to the conduction band, no possibility of flow of electrons, that will give you insulator. But if the valence band is completely filled, but the conduction band is not in the same region, but at the same time not very far, with a small energy gap in between, such that the electron can easily excite, then that will give you semiconductor. So, this is what the classification of metals into metals and crystals into what you call conductors, semiconductors and insulators. Then beyond this, what also we should discuss, of course, metals, conductors, all the metals, insulators, as we have many examples of non-metals, semiconductors, silicon and germanium, right. Like this we have different examples. Also we have oxides of metals, like if you take the case of titanium, titanium oxide is a conductor, titanium trioxide, from metallic conductor to insulator it transits, titanium dioxide is an insulator. So, like this, not only metals, metallic compounds like metal oxides, titanium oxide, vanadium oxide, chromium oxide, like this some of the metal oxides are also conducting. Then we have non-metals like graphite is also a conducting, and non-metal like diamond is insulator. So, like this we have both in metals and non-metals, we have the classification, we have the examples for both metallic conductors and insulators. Not only the elemental forms, even the compound forms like oxides, as we told now, can be conductors or insulators, right. Next what we have to go is dielectric properties. What is a dielectric property? Dielectric substances are the ones which they are divided into two dipoles when electric field is applied, but will not allow the flow of current, flow of charge. This is what we call dielectric substances. Then what is the classification in dielectric substances? What are the examples? That next we see. The dielectric properties. For that, what is a dielectric substance? Dielectric substance is one which on the influence of electric field will not conduct any charge, but because of the reason is that the electrons are held very tightly in the atoms, in that present molecular lattice. The electrons are very tightly held, so no electric field will be even in electric field we do not see any charge flowing across it. Such kind of substances is what we call dielectric substances. But when applied electrical field is there, then what happens is the substance of the molecule will get divided into differently charged poles. That is what we call dipole. Under the influence of external electric field, charges get separated to give dipole. to give dipole. As a result, the flow of the dipole, the movement of the dipole is the one that makes the substance to conduct current. Here there are two possibilities, that all the dipoles align in compensatory mode such that net dipole is 0. All the dipoles will align, means like this, all positive charges and negative charges, or like this, they will align oppositively. So, the net dipole moment will become 0, but the substance will become conducting. That kind of substances are what we call piezoelectric, that kind of piezoelectric current. This kind of substances, when applied to mechanical stress, when any mechanical stress or strain, if applied, or if pressure is changed, then current is produced. If mechanical stress or strain is applied or pressure is changed, then current is produced. Or if electric field is strongly applied, then there will be a deformation in the shape of the substance because it undergoes mechanical strain. Such kind of substances is what we call piezoelectric substances, and the conductance of that type of conductance is what we call piezoelectric current. Then another case is also there, pyroelectric current. The pyroelectric current is the one that is with change in temperature. There will be on heating the substance, there will be a flow of charge, and that is also because of this kind of disturbance in the alignment. Now, under normal conditions, if they align properly, then the net dipole moment is 0, but when an external electrical field is applied, then there will be a possibility of current to produce. But instead of that, if the similar kind of substance is heated, on heating what happens? Alignment changes. Then you will get different types of alignments. Random alignment. This is what we call random alignment. This random alignment of dipoles again will lead to charge flow. It will allow the flow of the charge. So, if current is flown on increasing the temperature because of which there is a random alignment of dipoles, then that is called. So, if the flow of charge or the conductance is observed on heating whereby alignment changes and flow is observed, then this is what we call pyroelectric current. So, it is pyroelectric current. So, if any mechanical stress is applied and current flow is observed, then it is piezoelectric current. With the change in temperature, if flow of current is observed, then what we call pyroelectric current. This is what is the difference. Under normal circumstances, the substances are not conductors, but when mechanical stress or strain is applied or when the temperature is increased, then what we call, then we get conductance. That kind of substances are called either piezoelectric substances or pyroelectric substances, or piezoelectricity or pyroelectricity. Besides all this, also we have something called superconductors. What are superconductors? Superconductors means the conductance is very high. The conductance is very high, superconductance. This largely we use in the modern day electronic equipments, electronic gadgets, and also for different other applications, right. Now, what are the superconductors and how do we get them? Superconductors, of course, as the name indicates, the conductance is very high. How is it possible? The basic principle of electric current and electrical conductance and the effect of temperature, if we go back, then it is well known that with increase in temperature, resistance will increase. Resistance will increase. As a result, conductance decreases. This is in metallic conductors. Here we are strictly talking about metallic conductors, but this is not true in electrolytic conductors. But here our discussion is only on metallic conductors. In metallic conductors, with increase in temperature, resistance increases, conductance decreases. So, on the converse, if temperature is decreased, what will happen? The resistance also will decrease. When the resistance decreased, what does it mean? Conductance is increased. So, as you keep on decreasing the temperature, if you reach to a stage of absolute zero, what will happen? Resistance will completely become zero. Resistance zero means what? That particular substance is becoming completely conducting. The conductance will increase enormously. So, some of the substances at the range of about 20 Kelvin, 25 Kelvin, close to absolute zero. Of course, absolute zero to attain it is very difficult. But 20 Kelvin, that is liquid hydrogen temperature, liquid helium temperature, at such low temperatures, the electrical resistance will be almost negligible. Then in such case, conductance will increase enormously. So, at that particular temperature, at such a low temperature, substances will exhibit this high conductance, what is called superconductance. Then which kind of substances normally we understudy? Yttrium, calcium, copper oxide mixture. Yttrium, calcium, copper. Bismuth, calcium, copper. These kind of oxides, mixed oxides, they are all mixed oxides. Yttrium oxide, calcium oxide, cupric oxide. Mixture of all the three will efficiently work as superconductors. They found a large number of applications in modern day electronic equipments, electronic applications, right. So, but about the superconductors, this is too early to study about superconductors in a later engineering part, normally about the working principles, methods of preparation and all about the superconductors in higher classes only that normally we deal. But at this stage, this information about classification of these solids into conductors, insulators, semiconductors, superconductors, again in that piezoelectric, for pyroelectric, all this basic classification, just the terms if we know and the basic principles, that is only that we have to look at it. So, with this, the electrical properties is what we have completed. Next, what we have to go to magnetic properties of solids. So, now we go to magnetic properties of solids. Now, we look at the magnetic properties of solids. Magnetic properties. Magnetic properties of solids. Well, a substance is said to be magnetic, or first of all, if it with respect to the magnetic moment or its ability to get it attracted into magnetic field or not attracted into magnetic field, or weakly attracted or strongly attracted. Based on this, we classify the substances according to their magnetic properties. Now, the magnetic property mathematical calculation, usually it is done by in terms of magnetic moment. Magnetic moment. that is mu is equal to root over n into n plus 2 Bohr magneton, where n is number of unpaired electrons. So, first of all, the basic point is that either for electrical properties or for magnetic properties, one necessary and sufficient condition is that there should exist free electrons, unpaired electrons. If free electrons exist, then the free flow of electrons will give us either electrical property or magnetic property. If there is no free electron, that is if n is equal to 0, then mu will become 0, magnetic moment is 0. That substance will not be attracted into magnetic field. So, based on the ability of a substance to get attracted into magnetic field, we define the substances as paramagnetic, diamagnetic, ferromagnetic, ferrimagnetic, antiferromagnetic. Antiferromagnetic. These are the different types. Let us see one by one. What is paramagnetic? First of all, paramagnetic substance means a substance should have unpaired electrons, magnetic moment is greater than 0, and it is weakly attracted into magnetic field, weakly attracted into magnetic field. Basically, that happens when the magnetic moment is relatively less. If the magnetic moment is relatively less, that means if it has less number of unpaired electrons. If we have less number of unpaired electrons, then it will be paramagnetic. Weakly attracted into magnetic field, and substance, it cannot be magnetized, means it cannot be converted into magnet, it cannot be converted into permanent magnet. It cannot be converted into permanent magnet, gets attracted into magnetic field, but that itself is not a magnet. Example, like vanadium dioxide, cupric oxide, oxygen gas, this is a non-metal. So, these are the examples. These are the substances which are having either 1 or 2 unpaired electrons. So, the magnetic moment will be either 1.732 or 1.414, or less than 2 is what actually we get it, or less than 3, because if n is equal to 1, then it is 1.732. If n is equal to 2, then it is root 5. If n is equal to 2, then it is root 8. So, it is less than 3. So, like this we get it. These are the substances that will have an unpaired electron, but less in number. They are weakly attracted into magnetic field, but they cannot be magnetized. They themselves are not magnets. They cannot be converted into permanent magnets. They are what we call paramagnetic substances. The next is diamagnetic substance. What is diamagnetic substance? A diamagnetic substance is the one which doesn't have any unpaired electron. Doesn't have any unpaired electron. That means n is equal to 0, implies mu is equal to 0. Magnetic moment is 0. And so, they can't be attracted into magnetic field they can't be attracted into, or they are repelled in magnetic field. Examples, we have many examples. Most of the non-metals like fluorine gas, chlorine gas, bromine, iodine, so on and so forth, all these are, or even other non-metals like carbon, all these are diamagnetic substances. And many of the compounds, most of the chemical compounds where octet rule is followed, most of the cases, again not in O2 case octet rule is followed, but according to MOT it is paramagnetic, and that is what practically it is observed. So exceptions are always there. So but in general these are all the diamagnetic substances. For diamagnetic substances the magnetic moment is 0, number of unpaired electrons are 0, they are not attracted into magnetic field, they are repelled in the magnetic field. These are what we call diamagnetic, right. Then what is ferromagnetic? Ferromagnetic is the substances where we have large number of the difference between ferromagnetic and paramagnetic is something very important. Ferromagnetic substances are strongly attracted into magnetic field, and they can be converted into permanent magnets. Which is the metal we use to magnet? Iron. So permanent magnets, iron, cobalt, nickel, chromium oxide, all these are what you call ferromagnetic, strongly attracted into magnetic field. They themselves can be converted on repeated alignment of, here the alignment of all the free electrons, this is the ferro, all unpaired electrons, dia. This is what is the difference. Here all unpaired, here all paired electrons, no unpaired electron. That is what is the difference between ferro and dia. Para is somewhat in between case, where you have less number of electrons, just only 2 or 1, this is para. But of course, let me warn you that there is no clear cut distinction that if you have only 2 electrons in the 2 unpaired electrons, then it is para, or if you have 5 unpaired electrons it is ferro. There is no any such condition, but this is a general notation, right. So here having more number of unpaired electrons and all having parallel spins, having high magnetic moment, we call ferro. No unpaired electron, all electrons are paired up, magnetic moment is 0 is dia, and somewhat a lesser magnetic strength, magnetic moment is para. Then what is ferri and antiferro? Let us see about them. That is, the antiferro is that here you have unpaired electrons. Unpaired electrons are present. Unpaired electrons are present, but the alignment of, but with opposite spins, opposite alignment, that is opposite spin. So it is like this, If one unpaired electron is having a positive spin, the other one will have negative spin, like this. So what is the net result is what? 0. You can have a magnetic moment with all positive spins will give you certain magnetic moment, all negative will give you certain magnetic moment, but one cancels the other. One cancels the other. That is antiferro. Examples like MnO, manganese oxide, Mn2O3, MnO2. These oxides of manganese are antiferro. They have unpaired electrons, but spin of one electron is nullifying the other one with opposite spins. So the net magnetic moment is becoming 0. So in spite of having unpaired electrons, but still the magnetic moment is 0 and behave as a diamagnetic. Behave as diamagnetic. That is what is called antiferro. Then what is ferri? What is ferri? Ferri is again having unpaired electrons. Here also you will have an unpaired electron, but some are with opposite spins, opposite alignment, like so the magnetic moment decreases. Magnetic moment decreases because here again you have many unpaired electrons, but some of them are having opposite spins. As a result, net magnetic moment is decreased. So it behaves like a paramagnetic, but having opposite spins. So this is what is called ferrimagnetic. Example, Fe3O4, ZnMg2O4. Okay, these are all the examples. So finally, it is not that for a substance to behave as a magnetic substance, magnetic material, even though we say that the necessary and sufficient condition is to present unpaired electron, but just because unpaired electron present does not mean that the substance will become ferromagnetic or paramagnetic, because in spite of unpaired electrons are present, but if the spins are aligned in opposite directions and gives a net magnetic moment 0, that will become antiferro and it will not show any magnetic property. Similarly, in the case if some of them are parallel and some of them are anti-parallel, then it will show a reduced magnetic moment. So the effect is less. That is what we call ferrimagnetic. So this completes the magnetic properties of solids. So with this, whatever all that is required within our syllabus, the solid state topic we have completed. All the best.